Now, as we continue with this unit, we're going to look at the graphs of equations. And in this process, we will actually use the graphing calculator that I hope you've had a little time to look at in the previous break. So, let's look at graphs of equations now. First of all, we need to decide what that means. So let me give you a generic definition of graphs of equations. So I'm going to repeat myself here to save a little writing. Graphs of equations, what is that? Well, what is the graph of an equation? It is the set of points, and remember, in the coordinate plane, in the plane that we have given coordinates and addresses, in other words, to every point, all the points are of the form x comma y. The set of points that, and here's one of those mathematical words, satisfy the equation. So the graph of an equation is the set of points x, y that satisfy the equation. And because these are points, you can graph them, and that's where the graph comes from. Now, why do we say satisfy? Well, the equation, as you'll see, is something that involves an equal sign, of course. That's the verb in the sentence that is an equation. And there will be x's and y's. And then when we put in the x's and y's that we get as the set of points, they satisfy the equation, meaning the equation becomes true when they're in there. So, for example, let me give you something to think about. Let's take an example. Here's an equation. Y equals 2x plus 5. And remember what I said about equations very early in the review. This equals is the verb, and the equation is a sentence. And you can see there's a y and an x involved here. Now, for the correct choices of y and x, we will get true statements here. Not all values will work. If I put in x equals 0 and I put y equal 100, that's not going to be true, because 100 then would be 0 plus 5, and that is clearly not true. However, we can go ahead and list in the form of a table. So I'll list x, y, and then I'll list the point x comma y. So we're going to build a table here. These are the kind of tables that you can see on your graphing calculator also. And I will just pick a few points, x, say 0, 1, minus 5, 10, etc. You have to realize there are an infinite number of real numbers to choose, so my choice is an arbitrary choice, and we'll talk about that later and how that will affect what the graph looks like. And then we'll calculate what y will be, because up here this equation gives us a formula that says if x is given, then y is 2 times that number plus 5. So if x is 0, y will be 2 times 0 plus 5, which means y is 5. If x is 1, then y is 2 times 1, which is 2 plus 5. That's 7. If x is minus 5, then y is 2 times minus 5, which is minus 10. Plus 5 is minus 5. And finally, if we put 10 in for x, we have 20 here plus 5. So y is 25, and we could continue that with any number of points we liked. Having an x and a y creates a point that we can then graph. So this is the point 0, 5, where the x value is in the first position, the y value is in the second position. That's what an ordered pair is. And then the other points are 1, 7, minus 5, 10, 25, etc. Now, I'm going to plot these points. I'm going to actually draw them, and then I'm going to try and produce a graph based on this really meager set of points. There are only 4 points after all. So, here is an axis system. And let me mark off in units of 5, because that seems to be about what I need. So I will go up 5 here, and then 10, 15, 20, and all the way up here to 25, because if you remember, I had a point that requires that. And then I will go down a few here and over a few to the left. I'll mark the first stage as minus 5 here and minus 5 here, and that may be all I need. So let me plot the points that were on the previous page. If I show you what those are, they are these 4 points, if you recall, 0, 5, 1, 7, minus 5, 10, and 25. Now I'll go ahead and plot those. Let me start with 0, 5. That's an easy one to remember. 0 is the x-coordinate, so there is no direction in the x on the x-axis, and then I go up to 5. so there's a point on my graph. The second point was 1, 7, so 1 is about here, and 7 is a little above 5, so it's about here. You can't do much better when you do this by hand, so there's an approximation of where that point should be. Then there was the point -5, -5, so it's -5 in both of the coordinates. That puts a point here. And finally, there was the point 10, 25, which puts a point up here. So there are the 4 points that I've graphed. And if I've done this carefully, you can see that when I connect them up, I have what appears to be, seems to be, a line. Now, you cannot judge the picture strictly by looking at 4 points. I warn you that this is dangerous. Okay, and I will give you more information on this coming up. But let's just take it for granted that 4 points is really not enough to determine a graph in general. If I knew beforehand that this was a line, then since I know Euclidean geometry only requires 2 points to determine a line, any 2 of these points would be sufficient to draw the line. But I don't know that that's a line yet. We'll talk about that later. So let me give you another example, a little more complicated one. Let's raise the bar a bit and look at this particular equation, y equals x squared. Now y equals x squared is a function that you may learn eventually is called quadratic. It has a picture that is a parabola. We don't need to know that now. We just need to know that in order to get y, we take x and square it. And if you create a table once again, I won't do too many of these, but I think another table at this point is appropriate. And we just pick a few points like -3, -1, 0, 1, 3, etc. for x. We know that what y is the square of this, because y is equal to x squared. So I just square these. I get 9, 1, 0, 1, 9, etc. There's a nice symmetry going on here. And so this will be the points -3, 9, -1, 1, 0, 0, we know where that point is, that's the origin, 0.11, 0.39, and there's an infinite number of other points. Now, if I plot these points, as I did the other points, on a coordinate system, and on this one, I will take the vertical scale to be in 5s again, so 5, 10, 15, and 20 I think is as high as I need to go. And I will take the x scale as 1. Now you might say, why am I doing that? Well, I can choose whatever scale I want on the x and the y axes. It is always your choice. And you choose a scale that is easy for you to graph what you need to graph. So if that's 1, 2, 3, and 4, and going to the left, of course, -1, -2, -3, etc. And I plot the points we had previously. Let me remind you what those were. -3, 9, -1, 1, 0, 0, 1, 1, and 3, 9. So -3 and 9, this is 10, so -3, 9 is about there. The next point was -1, 1. That will be about there, because this is about where 1 is, say. 0, 0 is the origin. And notice on the other side, 1, 1 mirrors the point -1, 1, and then the point 3, 9 mirrors the point -3, 9. Now when we connect these up, we get a very nice symmetric curve, we'll talk about symmetry later, that looks something like that. And that will become a very familiar curve to you as this course goes on. But let me warn you once again, this is dangerous. Plotting a curve by connecting points when you have so few points, or even in fact if you had 1,000,000 points, it would still be dangerous. You require mathematical knowledge to actually know that this is the graph and that there's not something else happening there. Now since that's sometimes hard to believe, let me now give you a classic student error, which I hope will make the point. So I'll even write that down. Classic student error. Now here's what a student will do. Of course, this won't be you, but here's what a student might do. Here is an equation I give you. Y is equal to x to the 4th minus 5x squared plus 4. Now that's a little bit more complicated than the previous ones, but it doesn't matter. Let's go ahead and plot a few points by first creating a table as I've done before. And I'll pick some easy numbers for x. say minus 2, minus 1, 1, and 2. Okay, those are easy numbers. Let me put them into y, and you might say, well, it's rather complicated. But assuming that I've done these correctly, you will see, for example, if I put minus 2 in, that y will be 0. For example, minus 2 to the 4th will be 16. Minus 2 squared is 4, so that's 16 minus 20. That's minus 4, plus 4 is 0. And it will turn out if you put minus 1 in, you get 0, 1 in, you get 0, and 2 in, you get 0. You can check those on your own, but that leaves you with points minus 2, 0, minus 1, 0, 1, 0, and 2, 0. Dot, dot, dot. You could say that this goes out to infinity, but maybe you feel confident plotting these 4 points. Okay, let's go ahead and look at what a plot would look like if you plotted those 4 points. If you do, it turns out to be a very easy plot. If this is 1, 2, and this is minus 1, minus 2, then the points on the x-axis that you plot are minus 2, 0, which is that point, minus 1, 0, 1, 0, and 2, 0. And so you would conclude that the graph, if you connected these dots, is the same thing as the x-axis. Now, the fact is, you have gotten this horribly wrong. In fact, the actual graph looks something like this. True graph. Nothing at all like the graph that you thought it was based on these 4 points. So, there is always danger when you don't plot all possible points, and since there are an infinite number of points, there's always danger. We need to have some other mathematical ideas that will tell us how the curve will appear, even though we know we can't plot an infinite number of points, even with a computer. So, that brings up the next question. What kind of a graph do we really want? And we're going to use a term for that that's become common now that we have graphing calculators. The definition that I'm going to write down is the following. A complete graph is the term we'll use. A complete graph. Now, what could that mean? Well, in short, it means a graph that contains, within the window you're looking at, all the interesting stuff about the curve that you're trying to graph. So a complete graph reveals all the important features of the graph. For example, peaks, valleys, flats, where the curve goes horizontal, and then other words you may know, asymptotes, etc. In short, there should be no hidden behavior. Now that is a tall order. And as I said, we cannot answer the question completely without some calculus. We can, however, make some strong inroads into it using what we're going to learn in this course. But that's exactly what we want to do. Complete graph reveals all the important features of the graph, peaks, valleys, flats, asymptotes, anything else of interest. So, since we're going to be using graphing calculators, before I go ahead and show you some examples on the graphing calculator, let me give you what one might call a general procedure for graphing on a calculator, say. This also applies, of course, to a computer algebra system. First of all, you want to write whatever your equation is as y equals something in only the variable x. Calculator is limited. It must have a variable on the left, usually y, but it doesn't have to be y, and only a single variable on the right. But it has to be separated out this way. Then what you want to do is pick a window. Now, as I said, and you saw earlier, window choice makes a big difference as to what you'll see. Once you've done that, You will then enter your y equals something from above. And I'll show you that by example with the calculator in a moment. And then finally, you'll graph it using the graph key on your calculator. So that is the procedure. The first part, writing this, has to be done by yourself beforehand. So let me start an example, and then we'll continue the example onto a calculator. Here's the example we're going to look at. 6x squared plus 3y equals 24. Now, as I said, I need to rewrite this so that the y is alone on the left, there's an equal sign, and everything else on the right involves x or constants. So this is just a matter of rearrangement. I'll move the 6x squared to the other side. So I'll have 3y here. I'll have 24 minus 6x squared. And then I'll divide both sides by 3. So y will become equal to 24 divided by 3 is 8. 6 divided by 3 will give me 2x squared. So this is the equation I am now going to graph. 8 minus 2x squared. So, on to the calculators. All right, here's the calculator. Now I'm going to walk you through the entire process. First, I will turn it on. You see I'm already in the graph mode. Let's hit the y equals key so I can type in the function, which is the equation that we are currently looking at. Function is actually a term we'll use later. 8 minus 2x, and this calculator is unlike any other. It allows you to type in powers the way you would write them. Notice that the superscript 2 is above, just the way you would write that by hand. So that's a nice feature that this calculator has. All right, I said the next thing I needed to do was pick a window, so let's hit the window key. Now I've given some thought to this window, so let me go ahead and type in first minus 5 to get x min, 5 for x max. The scale is 1, I will leave it that way. Y min I will make minus 10, and y max I will make 20. And I'll leave the scale, well, no, I think I'll change the scale to 2 for the y scale. So now I've chosen that. I've entered my function and I've picked a window. Now all I have to do is graph it. Well, I just hit the graph key, and lo and behold, you will see that the curve appears on the calculator. You may have noticed that it had a little blinking spot up here in the upper right-hand corner. That indicates that the calculator is busy, and it is busy graphing the equation. And so there's a picture. Now, I might decide that the window I chose is not a good window. I would like to improve this window a bit. So I might say the y is a little bit too high because I'd like to have the graph fill the screen a little bit more. So maybe I could bring that down. How would I do that? This is called experimentation, or fiddling if you like. Go back to the window, come down to y max, which was the top. I've gone up to 20. Let me see what it would look like if I changed that to 15. Go back and hit graph. Of course, the window has changed, so the graph has to be reconstructed. And you can see it seems to fit the screen a little better. Now this is the kind of thing you're going to do all the time. You're going to look at the screen and you're going to pick a new window based on what you see. You'll also change the window based on the kind of calculations that you do. And we'll learn about that later in the course. I wanted to show you a couple of other things while we're here, and we'll see this with other pictures later. There's a key here called trace. Watch what happens when I hit trace. Several things appear on the screen. In the upper left corner you see the function appears. Maybe a little hard to read. It says y1 equals 8 minus 2x squared. Now the newer calculators actually put the function up there. And on the bottom you see x equals 0 and y equals 0. Now if I use the arrow keys and I move away from that, look what's happening. Actually that wasn't y equals 0, was it? That was the top there, so that was y equal another number. But you see what's happening as the cursor is moving along, the x and y values below are changing because they are giving the coordinates of the cursor approximately. Those are decimal approximations, but this is a nice way to see. And let's see what happens if we come on down to the x-axis. We'd like at one point for the x value to be some number and the y value to actually go to 0. Now see, it didn't happen. Let me go back. At this point the y value, if you can read it, is positive. It's 0.12 something. The next stage, as I trace further down, I have minus 0.5. So it's clear that I've crossed the axis, but you won't always get the point that you're looking for. We'll have to talk about that later. And those are limitations of the machine, and there are ways to get more appropriate approximations. One other thing I wanted to show you while we're here is the table feature, which a lot of calculators now have. If I hit the table key, a table appears. And on the left there are x values, and you can set this table up any way you like. It is currently set up with integer values 4, 5, 6, 7, 8, etc. And look what's on the right, the y values associated with them. The top of this column is y1, and that's the function we entered, 8 minus 2x squared. And so if you put 4 in there, you get the minus 24 value there. I believe that's what that says. Yeah. And then you get the other values. And you can also see those numbers appearing below as I change this directly below the table. Y1 minus 154, minus 120, etc. is appearing below. And the other columns are for what? Well, if we have more functions, we can have a table in which all of those functional values are listed. We'll get back to this later. I wanted to give you some indication of what this would look like. Now, while we're here, let's go ahead and change the function to something more complicated and fiddle a little bit. And I'll show you something about zooming. So go back to y equals. Well, let's first go back to the graph, and then let's go to y equals. And I'm going to hit my clear key and wipe out that function. Now I'm going to type in one that's more complicated. X cubed, so you can see how it looks when you do this, minus 11x squared. See, this calculator is so nice because the powers appear above. Minus 190x, and then plus 200. Now that's a function with coefficients you probably wouldn't have seen before we had calculators to look at things, because those are big numbers, and that makes it hard to calculate with by hand. But with a calculator, there's no problem. Now I've thought about this a little bit, and we're going to have to experiment, but here's a starting point for the window. We'll go from minus 12, enter, to 1 to 12, and then the scale I will make equal to 4 for the x scale, and then I'll go from minus 200 to 200 in the y direction, and then the scale I will make 100. So let's see what the graph looks like when we do this. Now I purposely chose this so that the graph would not be a complete graph, that parts of it are clearly outside the window. It seems to go up on the left, come down in the middle, and it seems to disappear at that point. Now it looks like something's missing. And what you need to do is fiddle with this. Experiment. Now you can simply experiment by changing the window directly, as we've seen before. But there are some other features you need to know about. One is zooming. There's a key called zoom. I hit the zoom key. Now I have a variety of options. If you look to the right of zoom, I have an automatic zooming, which I won't do. I have zoom box, which I'll show you later, zoom in, which I'll show you later. But right now I want to look at zoom out, because I think I'm too close, and if I zoom back, if I move backward, perhaps I can see more of the graph. So I've got it set at zoom out. If I hit the enter key, it will now take the curve and zoom out, which means pull yourself backwards from the screen. And you see what's happening. You can see much more of what's going on, and you can begin to say, aha, I think I know what the shape of this is. It's not mathematically precise just yet, but we're beginning to get a feel for what this picture ought to look like. It looks like I ought to extend the y-min, the lower part, so that I can actually see more of the bottom here. There seems to be another valley down here. So let me go ahead and just change that window and come down here to y-min. Currently it's at minus 800. Let me go down to, say, minus 1,000 and go back to the graph and see if that gives me the valley I was looking for. All of this is experimentation. The more mathematics you know, the better you are at it, because you know where the valley will occur. And calculus helps you do that, but we will learn ways of doing that also. Now see, I didn't go far enough. So let's go back to the window, come on down to y-min, and be a little bolder, go to minus 1,500. And let's see, I want to get 1,500, there we go. And then go back to the graph, and now let's see if I've picked up that valley. It goes up, comes down. Well, I'm doing better. Let's go back one more time and see if I can pick that up. I'm going to be even bolder. I'm going to go to minus 2,500 this time. And go back to the graph. And I think this time I will probably have the valley I was looking for. This is the kind of experimentation you'll be doing. With more mathematical knowledge, you won't have to go through so many stages. But now I have what I think is a complete graph. And since I know something about this graph, the fact that it's a cubic, I know that there's one up and one down, and that's all there is to it. That is, again, something we'll learn later. All right. Well, I think that's enough for now for looking at the graphing calculator. I had talked about graphs of equations. Let's now look at intercepts. Now that is the word that's used when we cross the x or y axis with the graph. They are often called x-intercepts and y-intercepts. So let's go ahead and look at the two of these. Intercepts. Now these are useful to give you points on the curve that are easy to find. What am I talking about? Well, here are the axes, x and y, and here's a curve coming along here, like so. Now there's some nice points, if I'm trying to pick points out to graph, that are very easy to see. There's this one, this one, this one, and this one. Those are all places where the curve crosses the x-axis, and here's another one. There's one point up here where it crosses the y-axis. These are all particularly nice points. Why are they nice? Well, all of these points down here, all of these x-intercepting points, have something in common. If you look at them as an ordered pair, they'll have an x value of some kind depending on where they are. But what is their y value? Neither up nor down. The y value is 0. So this is x comma 0. They all have that form. The x's are different, but they all have the same form. That makes them particularly nice. Likewise, if I'm looking at this one y-intercept point up here, what form will it have? Well, it has a particular height, some y value height, whatever that is, but notice that it is not in either of the directions for x. So the x coordinate of this point is 0. That makes this point nice because one of the two coordinates is 0. That's the reason people look for intercepts, because there's a 0 involved, and 0 is nice to deal with. Now, if I have a picture, it's easy to find the intercepts. What I'd like to do is look at the equation and find the intercepts from the equation. So let's examine that procedure. Finding intercepts, and those are either the x or the y intercepts. Finding intercepts from an equation. Well, the key to doing this is something I mentioned when I talked about the coordinates. X-intercepts, what do they look like? They have the form x comma 0. In other words, the y value is 0, and then the x value is the number we need to find. So that's what we do. We let y be 0 in the equation, and we solve for x. And that's all there is to it to find the x-intercepts. We let y be 0 and solve for x. And if that works for x, if you're looking for y-intercepts, then you do a similar operation. You're looking now for points where the y value is some unknown number, but the x value is 0. And the same procedure works. Let x be 0 this time, and solve for y. And that's all there is to it. So let me show you that with an example. Here's an example. Here is an equation, y equals x squared minus 3. Let's first look for x-intercepts. Now I'm doing this without looking at the picture. Eventually I would like to look at the picture, but right now I'm not going to look at the picture. This is a calculation for points of the form x comma 0 that I can do strictly from the equation. So what was the procedure again? I let y be 0 and I solve for x. Well, here's my expression. If I let y be 0, I have 0 equals x squared minus 3. So I just need to solve for x out of this. That's fairly easy. I move the 3 to the other side, so I have 3 equals x squared. And then I can reverse that if I like to have my x's on the left. But then what I need to do is take the square root of both sides, and so I end up with x being plus the square root of 3 or minus the square root of 3, because either one of those squared gives me 3. And so I have my two x values. And so what are the points that are the x-intercepts that I was looking for? Well, one is plus square root of 3, 0, and the other is minus square root of 3, 0. Now we'll look at a picture on the graphing calculator of this in a moment. But let's go ahead and look at the y-intercept version. So this is continued. Let me write the equation down again. Y equals x squared minus 3. And now let's look for the y-intercepts. And you know what the procedure is now. Y-intercepts, we are looking for points of the form 0, y. So we will let x be 0 and solve for y. So y equals 0 squared minus 3. Well, this is much easier than the other one. Y equals minus 3. There you go. And so what is the one point here that is the y-intercept point? It is the point 0, comma, minus 3. So there we have it. We have found the x and y-intercepts. Now, let's go back to the calculator and graph this and see what things look like. So, here's the calculator. I first have to type in the expression as before. So I have x squared and minus 3 is the expression. I need to pick a window. Now my window is something that, again, you just try a few things. I've done a little bit of preliminary work here, so I'll try something fairly simple. Minus 5 to 5 in the x-axis, and I'll let the x scale be 1. And then minus 4 to 4 in the y, and I'll let the y scale be 1. And let's see what this looks like. So there's a nice simple graph that we've got out of this. Now remember what we found. We found that the x-intercepts were to occur at plus or minus square root of 3, comma 0. So let's see what happens when we trace this. I will hit trace now, and let me come down to the curve. Let's see, hit trace, I'm sorry, let me hit the trace button there. There I'm on the curve. Let me come up here to the right to the axis, and what number is appearing there around x? It's at 1.82 right now. If I go backwards a bit, it's 1.74. Go backwards a little bit more, that's where I've got 1.66. Somewhere in there is square root of 3. If you remember, square root of 3 is approximately 1.73, so it looks like that's really true. That is at square root of 3. If I come on down to the bottom, that's where it is crossing the y-axis. Let's see if I can get that lined up directly there. Oh, look, that works out perfectly. X is 0, y is minus 3. So the trace happens to give me the exact value this time. So sometimes that will occur, and sometimes it won't. Now, I wanted to show you something else while I'm here. We've looked at trace. Let's go back to zoom. Now, there are some other features of zoom. If we want to get a better approximation for square root of 3, for example, let me look at zoom in. Now, let me go back to the graph before I do that. And turn the trace on. And let me put my cursor up here toward the right. See, the cursor is rising up there to about where I need it to be. Now, that's about where square root of 3 is. Let me go back to the zoom key, go over to the right, come on down to zoom in, and I will hit enter to make this happen. So if I do that, what has happened now? I have zoomed in on the curve, and the zoom in screen has centered on where the trace left the cursor. Here's trace again, and there's the cursor, you see. And if I now look at the cursor, I've got numbers that are much closer. Look at that, 1.72, 1.70 if I go that way. If I go farther to the right, 1.74. All of those are closer than those numbers were before. If you continue to zoom in, things will get better. Now, let me show you an alternative way to zoom in. Zoom, and come over to the right and go to zoom box. This is one of my favorite aspects of the calculator. I hit enter, and notice nothing has happened. Well, I have to set the box up. This feature allows me to set the box, create an actual box that the curve will zoom in on. Now what I want to do is box the intersection of the curve with the x-axis. So I have to choose the corners of the box. I've put the cursor up there. That's about where I want the corner to be of one corner of the box. Now to make that corner stay, I hit enter. Now you don't see anything happening, but watch what happens when I move the cursor. When I go over to the right, it draws a line behind it. See that? And if I come down, it's creating a box. Now I create the box around the point I'm interested in, and if I hit enter now, the screen will zoom in on that box and give me perhaps a better approximation to that intersection than I had before. So let's do that. I hit enter, and I have zoomed in on that box. Of course, the picture looks more or less the same. But if I hit trace now, and I look around that point, look at that. It stays around 1.73, even when I go to the left and the right, because the scale is so fine at this point. And of course, you can zoom in as much as you want to get whatever scale you want. So these are features of calculators that I wanted to point out to you at this point. Okay, let's go back to the pad and I'll show you something else. I have to warn you that I do abbreviations, so let me go ahead and give you a couple of abbreviations so that you will understand what I'm saying. My abbreviations, I don't know how standard they are. There are a couple that you're going to see again and again. Here is one, WRT. What could that possibly mean? I write WRT with a line under it. What it is going to mean, it means with, here's the W, respect, there's the R, to. So I will say with respect to something, and I'll use this abbreviation. And I will also use EQN, of course, for equation. We'll be using this word a lot. And of course, you've seen other abbreviations I use already. But I wanted to point out these two because I'm going to start using those a little bit more. We've looked at graphs of equations and intercepts crossing the axes. Let's go on to symmetry of graphs. The idea behind symmetry of graphs, before I draw anything, is that if the graph is symmetric, then you only have to draw one part of it, and you realize that the other part, or parts, are identical to the first part. So you save yourself a lot of work. So let's go ahead and look at symmetry. And there are three standard kinds of symmetry that we look at. All of these will be a matter of noticing something and then writing down a definition that corresponds to what we notice. So let me show you visually what's going to go on here, and then we'll see if we can get an algebraic representation of that. Here is a graph I'm going to draw, and if I'm lucky, I will get this to look very symmetric. There we go. There's a graph. Now, if you think of this graph as having symmetry around the x-axis, this is the x-axis, you can think of the x-axis as a mirror, where the graph above is reflected in the mirror to the graph below. And so this is all one graph that has two halves, and there is symmetry involved. Now, how can we write down algebraically that there's symmetry? It's nice to see that symmetry, but I'd like to write it down algebraically so I can recognize it from the equation. And so that I will then be able to draw only the top and reflect that across the bottom and save myself half the work. Well, let's see. What would a point on this graph look like? Well, an arbitrary point is going to have coordinates x, y. So this is x, and this is a height of y. Those are the coordinates for the point. Now, because of the symmetry, if I come down here below, I know that this point is going to have coordinates, first of all, x, has the same x coordinate as the previous point. But since I have symmetry across the x-axis, if I've drawn this correctly, then it goes down the same distance it went up, which means the point here is x minus y. So the point over here is minus y. Well, that seems to be the key to recognizing this kind of symmetry. X, y lies on the curve if and only if x and minus y lie on the curve. So when we describe this, we say in English, that this is a curve that is symmetric with respect to, there's my little abbreviation, the x-axis. And you just need to think of the x-axis as a mirror. Now let me show you how the fact that xy and x minus y must lie on the curve for this kind of symmetry to be present will allow you to look at the equation and then see that there's symmetry without ever drawing the picture. So, I'll even write that down. So, x comma y and x comma minus y both satisfy the equation. And there's that abbreviation I promised I'd start using. So, what is another way to say that? Another way to say that, and this becomes the practical way of using this, replacing y by minus y does not alter the equation. That's the practical test that you will use. So this is the actual test that you can apply to an equation. You can look at the equation and everywhere a y occurs, replace it by minus y. If the equation as a result does not change, you have an equation that is symmetric with respect to the x-axis. So the example I'm going to use here and carry on to the next sheet is x equal y squared. So let me carry that on. X equal y squared. And let me see if this is symmetric with respect to the x-axis. I will replace y by minus y. Now you have to be careful that you do this correctly. The x doesn't change equals, the y up here is squared. So when I replace the y by minus y, the minus y is also squared. So you have to understand where the minus is going to go. It simply is replacing the y. And the y up here could have been thought of as y squared like that. So I'm now replacing the y by minus y, and I have to ask myself, is this the same equation as the one above? Well, of course it is. This is x equal, whether you square minus y or y, it's still y squared. Because the minus part is minus 1, square that, you get 1. So yes, it is the same equation as the original. So we have symmetry with respect to the x-axis. And if you look at the picture of this, I'll draw it up here in small. The actual graph of this looks like this. And you can see the symmetry with respect to the x-axis there. But this is a technique for checking symmetry without actually drawing the picture. Okay, good. That's symmetry with respect to the x-axis. Well, there's another axis, the y-axis. So let's likewise outline that procedure, perhaps a little more quickly. Suppose we have a curve. Here's the x-axis, here's the y-axis, and now the y-axis will be the mirror. And let me draw one, if I can draw something that looks reasonably symmetric here. There we go, that's fairly symmetric. And we ask ourselves, what is it that makes this symmetric with respect to the y-axis? Well, let's take a point here, x, y. Here's x. Here's the height y. And what is it that makes this symmetric? Well, the point corresponding to this xy across the mirror, across the y-axis, which would be over here, has what coordinates? Well, let's see. It has the same y-coordinate because it's the same height as the one to the right. And the x-coordinate is the same distance as it is to the right, except that it's now to the left, so this is a coordinate minus x, so this is minus x comma y. So the mirror makes symmetry from left to right, and we describe this, of course, as a curve that is symmetric with respect to the y-axis. And to give you an example, well, first of all, I'll go ahead and outline the same procedure as before. So you'll have this down. So xy and minus xy, both points satisfy the equation. So here's the test. replacing x by minus x doesn't alter the equation. So there is the test for symmetry with respect to the y-axis. And if we want to look at an example of this sort, here's one. Take the equation y equals x to the fourth minus x squared plus 1. And I'll carry that to the next page. And if you're thinking ahead of me, here I will copy it again. Y equals x to the fourth minus x squared plus 1. I'm going to replace the x everywhere by minus x. So here is the replacing. Replace x by minus x. What do I get? Y doesn't change. X is replaced by minus x, so that's minus x to the fourth now. Minus, this is where you be careful. This is x squared. I'm replacing the x by minus x and squaring it, plus 1. And you see that minus x to the fourth minus x squared, because those are even powers, will be the same thing as x to the fourth and x squared. So this is y equals x to the fourth minus x squared plus 1. So yes, we do have symmetry with respect to the y-axis. And here's the picture. You can check this out in your graphing calculator if you're looking for things to practice with. The picture looks something like this. It comes down here, goes up here, comes down here, and goes up like that. And you can clearly see the symmetry from side to side. So there are two types of symmetry. There is a third, and you may say, well, there are only two axes. Where is this third symmetry going to come from? Lastly, let me give you an example of the symmetry I'm talking about. This is a little bit different and perhaps unusual. You're used to thinking of mirrors as a line, or the mirror in your room that you look in. The same thing with this y-axis. You're thinking of a mirror from side to side. Now I'm going to talk about a mirror that consists of a single point, in this case the origin. And let me give you an example of a curve that one perhaps can see is symmetric in that sense. There's a symmetry across the point 0, 0 here. Because on this curve, if I take a point xy here, and I follow it through the origin to where it has its corresponding point on the other part of the curve, if this is x and this is y, you can see that this point must be at minus y distance downward and minus x to the left, so that its coordinates are minus x and minus y. And now you see why we've done this. Previously, we replaced y by minus y to get symmetry with respect to the x-axis, x by minus x to get symmetry with respect to the y. But if you replace both and you still have symmetry, this is symmetry with respect to the origin, this point in the middle. So this is symmetry, or symmetric, with respect to the origin. And the origin, remember, is the point 0, 0. So let me show you the procedure then for checking. You know where this is headed. So I will go ahead and just write it out. We want to replace x by minus x and simultaneously y by minus y to see if the equation is not altered. If it is not altered, then it is symmetric with respect to the origin. And a classic example of that is this particular function, y equals 1 over x. Now, of course, this only makes sense, let me put in parentheses, where x is not 0, because if x were 0, we'd have division by 0, and that doesn't make any sense, it's undefined. This curve will occur many times throughout this course. It has lots of features we're going to discuss. But let me go ahead and discuss its symmetry with respect to the origin, y equal 1 over x. I want to do the replacement now. And the replacement is to replace both y and x by minus y, and minus x, respectively. So I'll put a minus y here equals 1 over minus x. I just put the parentheses in to make sure you're clear that I'm replacing the x and y by their negatives. So I have minus y equals 1 over minus x. But you know that that's the same equation as the original, because if I multiply both sides by minus 1, I have y equal 1 over x. And so I haven't changed the equation. So this equation is symmetric with respect to the origin. Its picture is so important, I'm going to put it on its own sheet. We will see this time and again, so it's worth memorizing this graph. The graph looks more or less like this. It never touches the x or the y-axis. There are no x or y-intercepts, neither here nor here, here nor here. These lines simply approach the x-axis from both directions infinitely close but never touch. The same thing with the y-axis here. This is the curve y equal 1 over x. Clearly undefined when x is 0. There's no point on the graph here. And this is symmetric with respect to the origin, because if you take any point over here and you follow it through, there you can see there's a corresponding point there. You take a point up here and follow it through, there's a corresponding point there. So the symmetry is clear, and the fact that this has all of these interesting properties will be something that we deal with later. Let's look at another topic that deals with curves that are a little bit simpler. Let's go back to the list here. We've looked at graphs of equations. We've looked at intercepts, crossing the axes, and symmetry of graphs. Now, those are both techniques for producing graphs fairly easily. Let's now look at lines, the simplest possible graph. You call them straight lines, perhaps, in Euclid, when you were studying plane geometry in your high school years, but we'll just call them lines. And what we are going to do is define a property of lines that you could not have in plane geometry. This is a property that will be known as slope. But let's go ahead and get started on this. Lines. Now, in a plane, like the plane you studied in Euclidean geometry, in a plane, there is no measure of slantedness for a line, because there are no references. There are no reference points. There's no horizontal, there's no vertical. However, in a plane with a coordinate system, like our plane with the rectangular coordinate system, and in our case that's x and y axes, lines have what you might refer to, say, if you were beginning to think about this, as slantedness. And the slantedness is with respect to the axes. The idea is that if you have a line, then the only way that you know it is slanted is if you have some reference line and you can somehow see that it is slanted with respect to the reference line. And that's what we're going to discuss. Now, slantedness is too long a term for one thing, and it's not the term that is currently used, but there are a variety of words that convey this idea that you've probably run into in your life. Here are some of them. Grade. If you've ever driven on a road, you might have seen that the grade is often marked, and that is simply the degree of slantedness of the road. You might have seen the word pitch. Carpenters use this when they talk about the roof, a pitch of a roof, for example, or the pitch of a staircase that they're building. That is simply a slantedness of that with respect to the horizontal. In Europe, slantedness is often referred to as gradient. But the word that we will use, and is most commonly used for this, is slope. And so, since we have this idea, let's go ahead and see if we can come up with a definition that will make us feel satisfied. An actual mathematical definition for slope. So now, since I said we needed the references, the x and y axes, here they are. And let me draw a line here of some kind. So this is a line. And now I want to know how slanted is it with respect to these axes. Well, the first thing is we're only going to compare it with the x-axis, the horizontal. We can choose either axis we like, but we're going to choose the x-axis because that's conventional. And to measure the slantedness, I'm going to use a fact about lines that you may remember from geometry. Everything about a line is determined if you know 2 points on the line. 1 point is not enough because the line could twist around that point. But once you've picked out a second point, the line is fixed. That's the nature of lines. So let's suppose we have 2 points on the line, x1, y1, and let's call this one x2, y2. Now those are the coordinates of those points. Then, we've done this before when we talked about midpoint and the distance between points, but the same kind of argument will now bear different fruit. If we go horizontally here until we are right below the point x2, y2, and then we go vertically up to this point. So say horizontally, I'll put an arrow that way, and then vertically up this way. You can describe our path as follows. You can say that this was a run. Horizontal distance traveled will be referred to as a run, and this could be referred to as a rise. Now, these are words that are very commonly used, and you'll see them used again. What exactly is the numerical value of the rise in this case and the numerical value of the run? Well, that's easy to decide because we've done this argument before. The coordinates of the corner point we know. What is the x-coordinate here that corresponds to this point? Well, it's the same as the x-coordinate of the point above, so that's x sub 2. What is the y-coordinate of this point? Well, it's the same height as this point over here, so that must be y sub 1. And then as we did before, in the review, or in the beginning of this unit, excuse me, the distance between these 2 points is the x2 minus x1 values. The rise is similarly calculated. It is the distance between these 2 points, which refers to the y values, and that will be y2 minus y1. So now we've quantified the rise and the run. And the slope, the slantedness, will be described in terms of these 2 numbers. As you move along, how high do you rise, and that will determine how slanted you are. Now let me give you one warning. Rise is used interchangeably with what we might call fall. If we had a line coming down this way, and we went over to the right and then went down, you'd probably want to call that fall. But it is referred to also as rise. So let me do this. Plus or minus. Rise is either a plus or a minus number. And that would take into account a fall, because this is a line where there is a positive run and a negative rise. Okay, getting back to what I've discovered up here, I'm going to use these 2 numbers now, and I'm going to describe what I call the slope of this line. And here is the definition. And I'll give you several different forms of it so that you'll see what it actually means, I hope. The slope of the line, and of course I'm referring to the line I drew on the previous page, is, well, first of all, the commonly used letter for slope is m. That seems to have occurred for historical reasons. No matter, it is the letter that's used, so we will use it. Now, I will describe it to be the vertical rise, which remember could be plus or minus, over the horizontal run. Some people just say rise over run, but I wanted to emphasize the vertical and horizontal here. Now, there's another way to say that. The rise, if you remember from the previous picture, the rise was the difference between these 2 y values. You might say that in going from here to here, the y value has changed. There was a change in y. And in going from here to here, there was a change in x. So I can describe the run as a change in x and the rise as a change in y. So I can write that down. Change in y over change in x. Now, there is a symbolism for that. If you haven't seen this before, here it is. The Greek letter delta is used for change in, and we write delta y over delta x. So the words change in are translated into this symbol, delta. That's a delta. So change in y over change in x. This will lead you on to some of what we do later in college algebra, but it'll also lead you on to calculus. But there's one notation. And finally, to use the letters I used on the previous page, what is the change in y exactly? It's y2 minus y1 over x2 minus x1. It is the difference of the y's over the difference of the x's. And let me point out an obvious algebraic fact. If I reverse these two, that's the same as multiplying this through by negative 1, isn't it? Because then this would become negative y2, positive y1, and I could write that as y1 minus y2. Now if I multiply the bottom also by negative 1, I'd have x1 minus x2. But then I've multiplied the top and the bottom by negative 1. That's like multiplying the whole expression by 1. Negative 1 over 1 is just 1. So this expression is the same as this one. So all that matters is x2 and y2 are the first two numbers used, and x1, y1 are the second, or the x1, y1 are the first and the x2, y2 are second. As long as you're consistent, you can calculate the slope either way. Now there's something else here that's hidden until you take a pause and look at this. The slope here is defined as a quotient. Now there's a perennial problem with quotients. The bottom of the quotient is always a problem, because if the bottom of the quotient is ever 0, the quotient is undefined. So if we want to be careful here, we have to say one other thing. We have to say that x1 cannot be the same as x2, because if x1 and x2 are the same, the bottoms become 0. Now what would that mean graphically? Well, let's see. Note, when x1 equals x2, what happens graphically? Well, let's see. If we have a picture like this, and this is that point x1, which is the same as x2, so that's the same x value, then if we have 2 points that have coordinates x1, y1, and x2, y2, and x1 and x2 are the same, then we have a line that's vertical. That's a vertical line. That's what happens when x1 and x2 are equal. Now coming back to the definition of slope, that means that slope is undefined if we have a vertical line. Why would that make sense? Well, ask yourself, if this is the x-axis and this is the y-axis, just how slanted is this line? In a sense, it's infinitely slanted. But we will say that it has no slope. No slope. Because the slope requires that we have this difference on the bottom, and that's 0. Another way to say that is to say that it has an undefined slope, or rather that the slope is undefined. So no slope is indicated for vertical lines. So they are a separate category of lines. But apart from vertical lines, every other line has a slope. And just to repeat what we saw on the previous page, any 2 points determine the slope of a line. Because if you remember, we had slope was equal to the difference of the y's over the difference of the x's, and that only requires 2 points. Now, just to give you a sense of what slope means in the picture, remember when we drew the picture originally that we had a run that was positive because the x2 was greater than the x1, so this distance was positive. And then going vertically, we had a rise that was positive because the y2 and the y2 is larger than the y1. So if you took the rise over the run here, you take a positive number over a positive number and get a positive slope. Now, since we move from left to right, the x values are increasing as we go to the right. Remember, we have 1 and 2 and 3, etc. As we go from left to right, it appears that when the slope is positive, the line is rising to the right. And that gives us the clue as to what the number slope will mean to a line. So let me go ahead and give you the summary of what that will be, and then we'll look at some examples later. M, the slope. If the slope is greater than 0, the line is going up, and up for us means from left to right. If m is equal to 0, you might say that this is flat, or you might say horizontal. Either one of those is an accurate description. The line has no slope, because think about it. How can a slope be 0? Slope was determined to be y2 minus y1 over x2 minus x1. That was defined to be slope. Well, the only way a fraction can be 0 is if the top is 0. And the only way the top can be 0 is if the y1 and the y2 are the same. And if they're the same heights, the line must be horizontal. Finally, if m is less than 0, this indicates a line that is going down from left to right. And then let me put in the final case, m undefined. That was the case where we had division by 0 up here, where x2 and x1 are the same, and we've already decided that that meant you had a vertical line, which I suppose I can draw like this. So, here are all the possibilities for slope. Positive slope indicates a line that grows toward the right. Slope equals 0 is a line that is flat or horizontal. Less than 0 means the line goes down, and if the slope is undefined, it's a vertical line. All right, let me do an example of a problem here, just to give you a taste of how one might calculate with such things. For example, you might be asked the following. Graph the line through a particular point, say the point 3, 2, with slope, say m is equal to minus 4/5. So you're given a point on which to anchor your line, and then you're told a given direction. Since it's negative, it's some sort of direction going downward. And with a point and a slope like that, you think you ought to be able to draw the line. Now, eventually, we'll have an equation for all of this. But right now, we actually have to draw the picture. So let's go ahead and do that in our solution. The point we're going through is 3, 2, so we need to have at least 3 and 2 marked. 3 is the x value, 2 is the y value. So there's the point 3, 2, marked on the coordinate system. This is the x-axis, that's the y-axis. And now, how am I going to use the slope to get another point on the line? Because I need 2 points on the line to graph it. Well, the slope is rise over run. Now let me point out something here that's algebraically simple, but gives you options. I've written it with the minus on the top. I could also have written it as 4 over minus 5. So the minus could be on the bottom. It is the same fraction, of course. This way I have a run of 5 and a rise of minus 4, which would be a fall. Here I have a rise of 4 and a run of minus 5. Now my personal preference is to keep my runs positive. So I'm going to go 5 to the right. So I need to go 1, 2, 3, 4, 5. That'll take me to 8. From the point 3, 2, I go a distance 5. That's the run. The rise is minus 4, so I'm going to drop down 4. Now I'm 2 above the axis. I will have to go 2 below to drop down 4. So this is minus 4, and this is the rise. This is a negative rise. Now I have a point. What point is that? Well, let's see. The x-coordinate is clearly 8. The y-coordinate is 2 below. That's minus 2. Well, now I have this point and I have this point, and of course, graphically, I just need to connect the two, and I have the line drawn. So there's the graph of the line. Eventually, we'll talk about the equation of this line. Now, before we get to equations of lines, there's one last technical note I'd like to make, and I then will show you something on the calculator. So let's call this a technical note. You will find in your textbook and elsewhere reference to what are called square screens. Now, what does that mean? Remember what the screen of a calculator looks like. It's not unlike a television screen. It is longer horizontally than it is vertically. So if I do have an axis system and I mark off the same number of units on each direction, I might find that my x units, all of indicating a space of 1, look like that, whereas in order to get the y units in here, the same number, I have to squash them together a bit. So maybe a y unit of 1 looks like this. Now it's a little hard to tell. That's a little bit smaller than this. That's not a square screen. Square means that it looks like a unit here and a unit here are identical. Now, how would you create such a screen? Well, it really requires that you know the ratio of the two sides, the horizontal and the vertical sides. Now, that's not always clear. Some calculators have a key that allow you to set the screen to either a square screen, so a square screen setting, or sometimes it's referred to as a default screen setting. But not all calculators have that option. But now you have to ask yourself, is that really that important to me? Does it matter that the units on the x and the y axes look alike to me? Well, sometimes it does. If you're trying to draw a circle, for example, you like the circle to look like a circle and not be squashed in one direction. But that really is an aesthetic preference. It doesn't change the nature of the equation or the fact that this is a circle and all the points are equidistant from the center. It just looks funny. So for circles, perhaps that's worthwhile. For everything else, it doesn't matter so much. Let me show you something on the calculator now that will illustrate how different the same function, the same equation will look. So let me go to the calculator now. And turn this on. You'll see I'm in the area where I enter the equation. I have 3x entered. That will turn out to be the equation of a line. I've already picked a window, and let me show you what the graph looks like. Now here's the equation of that line. I am not going to change the equation of the line. All I'm going to do now is change the window. Now remember how that looks. It's a line that slants up. It's a line that goes up to the right, so the slope is a positive number of some kind. Let me go to the window and change one thing. I will change the x and the y value, the x min and x max values, excuse me. So minus 10 for x min to 10 for x max. Notice again that I did not change the equation. Let's go back to the graph. It looks like it's much steeper than it was before. It's not. It just looks that way because I've changed the window. Let me change the window one more time to make another dramatic point. Change the window. I will change the x min to minus 1 and the x max to 1. And now let's look at the graph. This graph is much shallower. It looks like it is not nearly as steep as it was before. But in all cases, it's exactly the same equation. So the moral is, if your window is different, your equation may appear to be different. If there's a certain way you'd like this equation to look, what you need to do is to pick a window that makes you feel comfortable. But mathematically, it doesn't make any difference. When we come back from this little break, we'll go and look at the equations of lines. So for the moment, let's take a pause.